Uh, Welcome to the chapter 2. In this chapter, we will discuss limits of functions. Uh, in this video, we'll cover limit of a function. So we define it and mention few limit laws. So let's get started. So objectives. Uh, I'll try to describe limit of a function. Then I'll provide some laws, some properties. And then in special case, we'll discuss how to compute limit of polynomials and rational functions. Finally, I will end with Sandwich Theorem and an example of its application. Okay, so what is a limit, right? What do we mean by a limit? So let's start with an example. This is the example from the book, if you like. So f of x. Let's say I want x squared minus 1 divided by x minus 1, right? So the question I want is what happens near x equal to 1, right? I mean, if I let x equal to, you cannot let x equal to 1, right? So x cannot be 1, right? Because if you let x equal to 1, you will get 1 minus 1, 1 minus 1, so it would become 0 over 0, but you cannot divide by 0, so it means you cannot let x equal to 1. However, we can ask the question near, right? So when x approaches to 1, it doesn't hit, but it approaches. So which means, so x approaching 1. What does that mean? It means x getting very close, right? So basically it means, so this is how we say, so meaning x is very close, so it could be close to 1. It's like 1.000000001, or it could be x is equal to 0.999999999, etc., right? So it's getting very close to 1, and then we want to find out, then it's okay, right? The function is defined and we want to find out what is f of x near 1. Well, for this occasion, it's okay. I mean, you can we can do as follows. Uh, we can do as follows. I can simplify, right? I mean, it's difference of square. So x squared minus 1, x minus 1. I can write it as x minus 1, x plus 1 divided by x minus 1. So x minus 1, x minus 1 cancel. Indeed, what I get is x plus 1, right? So this is my function, right? So that's my function. Now, if x is close, so if x is close to 1, then what happens to the x plus 1? Well, x plus then x plus 1 is close to, because you're adding 1, it's close to 1 plus 1, which is 2, right? So for example, if you take x equal to like a 0.999, right? Then what is x plus 1? It's 1.999. So it's very getting closer to 2. And similarly, if you let x is equal to like 1.0001, x plus 1 will be 2.0001, which is close to 2. Okay. Okay, so we see that this function near x equal to 1 approach to 2, right? So now we can informally tell you what limit is, what we mean limit. So in general, right? So here we can say, so we say for this example, we say that f of x approaches approaches to 2 as x goes to или approaches to 1, right? For that example. And we can also write it as a shorthand. We can write it as limit as x goes to 1 of f of x equal to 2. That's pretty shorthand. Now let's somewhat informal define it, right? So informal definition of a limit. So we say that f of x, like I wrote above, f of x approaches L. So L is my 2, right? Limit. We say L as x approaches to some number c, if so if what if uh, we can make if we can make f of x very close, whatever very means, very close to L, as close to L as you want, very close to L, by making x very close to C, right? So in this occasion, again, we write what? We write limit as x goes to C of f of x is equal to L. Okay, so that's how we write, and that's what we mean by this, right? So I can make f of x as close to L as I want by making x very close to C, right? So I'm controlling x. I can control f of x by controlling my x. Okay. Okay. Now let's do some examples. Some examples. It's a very easy example, but important somewhat. Let's look at an f of x is equal to just x, right? And what happens? So you can look at okay. You can also analyze it looking at the graph, if you like. Here's my x-axis. Here's my y-axis. So if you sketch this graph, y is equal to x. Let me pick a different color. So you get something like this, right? So this is y is equal to x. That's the function, right? Here it's 45 degrees, etc. So now if you pick any point C here, right? If you let x equal to C, what happens to y? Y is also C, right? So it means if you approach to C, if you let x go, so if you let x go to C, right? This symbol implies, so if x goes to C, then y, which is your f, right? Which is your f, goes to where? It also goes to C, right? So in other words, we can write limit as x goes to C, my x, this function f of x, goes to C, right? So for example, if you pick C equal to 1, so limit, or let's say x goes to 20, then this f of x is equal to x goes to 20, right? Another example is, what happens for the constant function, right? Let's say that f of x is some constant. Let's call it a, right? Some constant. So if you want to see it graphically, here's the graph. So you have some a here, and the graph is horizontal, right? It's constant. It's horizontal. Sorry. So this is y is equal to a constant, right? Here is a. There is an a. Okay, now again, if you pick a limit point C somewhere, right, in your x-axis, what happens? If you approach to C, so again, if you let x come close to C, so what do we mean? So you're picking points that are approaching to C. From left, you pick some points approaching from right, etc. Then what happens? Well, you are approaching to this point, right, which is A. So then your f of x, which is y, is approaching to A, right? It doesn't matter what C is. So basically, limit of as x goes to C of a constant function A is A, right? So limit of a constant function with constant A is A, right? Uh, right. How about non-example? So non-example. So non-example means cases when limit doesn't exist, right? For example, you can pick f of x is equal to 1 over x, right? And ask yourself, uh, what is the limit as x goes to 0 f of x, right? Well, you can again try to sketch the graph. So let's just sketch the graph when x is positive, but you can also sketch the, so here's my x, here's my y. So, so the graph looks something like this, though. Because as x increases, your function decreases, right? So I have a decreasing function here, right? But I'm trying to approach 0, right? I'm trying to approach 0. So here's 0. Here's my 0. So you're trying to move along x-axis. So when you move along x-axis, you're moving along x-axis. How are you moving with the function? So here's, right? Here's, you're moving in this direction. And it's going to infinite, right? So infinite is not a number. So we say the limit doesn't exist. So uh, lim f of x as x goes to 0, this the DNE, which means does not exist. Okay, does not exist. Let's do another example, which is known as step function. So you can look at the, let me just sketch the graph and then we will come with, so let's say, maybe I pick, let's say 1, right? So let's say 2. So let's look at this function right here. So let me pick different color. So this is the graph. Here it's nothing more. So let's say that here it's open. Here it's, let's describe this function, right? So how you describe this function? Let's call it g. So g of x. So it has sort of different behavior when x is bigger than 1 and then x is less than 1. But because I included less than 1 here, somehow I make this equality here. So when x is bigger than 1, what happens? If you're bigger than 1, what are the values? It's always 2, right? Here is always 2. If x is less than or equal to 1, here, I'm right here at the bottom, so this is 0, right? That's the function. It's like almost constant, but it has two values, 0 when x is less than 1, and 2. Okay, now if I were to find the limit of x as x goes to 1, right? Because 1 looks an interesting point of g of x. So what happens? Let me pick different color. So if you're somewhere here, you see I'm trying to approach 1, right? So I need to approach 1 from different parts. So if I approach limit from above, let's say, so we'll come to the right the one side limits next, but for now just approaching 1, then I'm moving on this line, right? So it means I'm approaching to 2, right? But if I'm sort of moving from left, from below, then I'm 0, right? So for example, if I let x very close to 1 but slightly bigger, what is my g of x? It's I'm in this occasion, right? It's still bigger now, so this is 2. I'm approaching to 2. But if I let x equal to like 99999, so it's very close to 1 but slightly less, then I'm in this situation, right? So this implies what? This implies my g of x in this case is 0, right? Because I'm 0 case. So you see, uh, when you approach one from different directions, it's 2 and 0. Well, limit cannot be two different things. So again, this doesn't exist. So we say that this limit does not exist. Okay? So the limit needs to be unique. It cannot be two different things. Okay. Now in the next, we'll discuss limit laws. So some properties limit, because you cannot always sort of use your calculator, right, in each time. Like you try, let's say that you try to approach x equal to c, you pick something very close and so on and so forth, try to estimate. So this is time consuming, right? So we need to have some properties that kind of simplifies our life when it comes to computing more complicated limits of more complicated functions. So far we just handled very simple functions. Okay, so my x is approaching to c, my f of x is L, and let's say that I have two different functions, so my f of x and the g of x, let me pick a different color, right? So I have f of x and g of x, so they're approaching to the same point, they are to the same point, but they have different limit. One, f of x is approaching to L, g of x is approaching M. Now here the first one is sum rule, so you see, I need to use the same. So if x equals to c, if I look at f of x plus g of x, so the sum of the two functions, then the limit is just L plus M. Okay, so limit of the sum is equal to sum of the limits. That's how you could remember. And the same applies for the difference rule. So the second part, second one, uh, it's the limit of the difference is difference of the limits. So f of x goes to L, g of x goes to M. Then when you take the difference, it goes to L minus M. Okay. What is the constant multiple rule? So you pick some k constant like 5, 2, minus 5, pi, whatever, some constant. If you multiply it by a function, this becomes a new function, right? K times f of x. What happens to the limit? Well, it becomes just k times the limit of the function f, right? F goes to L, so this is k top. Another uh, uh, the product rule. What's the product rule? If you multiply the two functions, it becomes a new function. If you take the limit becomes just the product of the limits, right? L times M. So everything is straightforward, right? It's very intuitive. And if you look at the quotient, f of x over g of x, then limit goes to L over M, provided M is not 0, right? If M is 0, then it doesn't exist, right? Now here's the power rule. Power rule, you take a function f of x, you raise to the power n. So it means you multiply f of x by n times, right? F of x times f of x times f of x. Then what happens to the limit? Limit also gets multiplied, right? L times L times L, etc. So it's really coming from this property, right? So L to the n. And similarly, if you take the nth root, right? If you take the nth root of x, then it becomes nth root of L, where you want to pick, okay, n is positive, etc. Right? If n is even, then f of x must be positive, right here, because it cannot have negative, so etc. Right. Let's do an example. Examples. So first, let's say that I want to find limit as x goes to, let's say 2, x squared minus 2x plus 1, right? Something like that. So limit of this function. So we know that the sum of the limited limit of the sums, etc., and the difference also, so we can write in the following form. So this is using the first two properties, right? So first two. So I'm using these two properties. Here you get like x squared. So first one is I will write slowly, then we can do minus here limit x goes to 2x and limit x goes to 2 1, right? But then what happens to the x? What is the limit of x squared? Well, here it's the uh, power rule, right? So if you know the limit of x, then you can just square it. So this becomes, it becomes like limit x goes to 2x, and then I can square it. Minus, what is the 2? So here, you see I'm multiplying, so you can take out the k. So I can write it here, instead of k, I have 2, right? So I can make it like minus 2 times limit as x goes to 2, x, plus we know what is this limit? This is limit of 1. What is 1? 1 is just a constant function. So it is just 1, right? Okay, now what is limit of x? Well, this is x. So I get x squared minus 2. Sorry. Instead of x, I have 2. Sorry. Uh, so here's 2 squared minus 2 times 2 plus 1. So this is 1. Okay, so that limit is equal to 1. Uh, let's do something about quotient. Let's again approach the 2. Let's pick the same function, x squared minus 2x plus 1, because we already know what it is. And let's divide by x plus 5, for example, right? So now again, if you go back to the quotient rule, it says you just need to compute each limit separately and then just divide it. So, which means you can take the limits, you can sort of split the limits, right? So here, and do the same here, place limit here, x plus 5, so let x goes to 2, let x goes to go to 2. So what happens at the top? Well, from 1, we already know that this is equal to 1. Now, if x go to 2, what is this? This is like limit of x plus limit of 5. Limit of x is equal to 2. Limit of 5 is equal to 5. So this is like 2 plus 5. So this is 1 over 7. Okay? Maybe we can, so which one is left? So we kind of did cover it all. Okay, we have product. Yeah, product is like power. So maybe you can do, okay, let's do what one root, right? So we can do, for example, if you let limit x goes to, let's say 1, square root of x squared plus 5x minus 2. I hope it's positive. What is this? So by this quotient rule, not the quotient, sorry, the root rule, you can take the root outside, take the limit inside, right? X1. So you swap the limit and the root. X squared plus 5x minus 2. And then apply the rules of the limit. What is this? This becomes like 1 squared plus 5 times 1 minus 2. This becomes 6 minus 2 is 4. We forgot the square root. So this is in fact 2. Okay, so that's pretty much the examples. You will do more examples in practice. So now that you saw the we already saw an example, right? We had an polynomial, right? Like x squared. So we had this x squared minus 2x plus 1. What is this? This is an example of a polynomial. What we really did here, we just make x equal to 2, right? So okay, I mean, in reality x is approaching 2. It's not equal to 2, but at the end when we compute the limit, it's you assigned, right? So you see here it's x squared, so we squared 2 minus 2x, we substituted x equal to 2, so it's 2 times 2 plus 1, right? It's like evaluating the polynomial. And for the rational function, this is called rational function right here, right? So rational function means polynomial divided by another polynomial, right? It's the quotient of the polynomial. So it's again, we just evaluate, right? If you let x equal to 2, so it becomes like 1 over 7, right? So that's what we want to say now. So first one, limit of polynomials. So if you have a polynomial, so this is sort of general form of polynomials, and if you let x equal to c of this p of x, then it's just equal to pc, p of c, okay? So you just set, you let x equal to c, that's all. You don't try to approach it. It's just x equal to c. So this is very simple, right? Limit of rational functions. So if you have a px and a qx, two polynomials, and the q of c is not 0, then as limit x go to c, p of x qx is just p of c divided by q of c, again provided the denominator is not 0, right? Yeah, I mean we can do examples, but it's not okay. Okay, let's do some examples. So limit as x goes to 5, uh, x cubed minus 3x plus let's make a square, 2x minus 100. What is this, right? You just let x equal to 5. So this is like 5 cubed minus 3 times 5 squared plus 2 times 5 minus 100. So I'm not going to compute it. If you like, you can do it. Let's do another example with the quotient. So let's let x equal to -1. Let's look at some polynomial x cubed minus 5x plus 10 divided by, now for the denominator we need to pick something that is not 0, right? Let's do x to the power 4 plus 2x squared minus 2, right? Minus 2. So what is it? Again, you just substitute. So this is like -1 cube minus 5 times -1 plus 10 divided by -1 to the power 4 plus 2 times -1 squared minus 2. Well, this is easier, so we can compute. So -1 here is plus 5 plus 10 divided by 1 plus 2 minus 2. So it just becomes, I think, 14, right? That's all. Okay, sandwich theorem. Sandwich theorem. You see the picture of sandwich. So it's sometimes very convenient to you bear in mind the sandwich theorem when you try to obtain limits, some important limits like limits of sine, etc. So what it says is following. Let's say that I want to compute. So you see, my goal is to compute this limit of a function when x goes to c. And what do I know about the f of x? Let's say that I can sort of bound my f of x from below by g of x and from above by h of x. So I'm sort of sandwiching, right? So this is like my h of x, h. This is like my g, and whatever I see inside is f, right? So I'm trying to sandwich from two sides. And let's say that surprisingly, let's say that if the limit of g of x and h of x they happen to be L, so they're approaching to the same limit, then f of x cannot escape, right? It has to approach to the same limit, right? If the upper bound and lower bound are approaching to one point, then there is no chance, but the middle f of x has to approach the same. So that's the sandwich theorem. So let me do one important sort of result out of this is the following. So let us take an example. If limit as x goes to c of f of x in absolute value. So I make up a new function, right? I have an old function f of x. I took the modulus absolute value. It becomes a new function. If this is 0, then limit as x goes to c of f of x is also 0. Okay, this is kind of some small theorem. So here you can try to, here is, if you like, a quick proof. What do we know? Well, we know that f of x is always between is less than the modulus of f of x, and it's also less than, sorry, it's bigger than f of x minus of the modulus, right? So any function is lies between negative of the absolute value of itself and the absolute value of f of x. Okay, uh, but what do we know? F of x, limit of f of x. So now as x goes to c, what happens to this one? Well, by given f, right? This is given. We know it goes to 0. If it goes to 0, negative of that thing also goes to 0, right? So this also goes to, it goes like -0, but it's 0, right? No, so by Sandwich theorem, they both, so this is my L, right? So this is my L, this is my L. So this means my midterm, the my f, which also has to go to 0, right? By Sandwich theorem. Sandwich theorem. Some people also call it squeeze law. Squeeze. It's squeezing, right? So let's do one more example. Limit as x goes to 0, sine of x, right? Trigonometric function. This is 0. Y, right? Well, we are using one fact. So you can look back to chapter 1. We didn't cover trigonometric functions, but if you look at the trigonometric function, there you can find proof. But I will also give it as an exercise for the next week homework 2. So the fact is sine of x is always less than x for all x. For all x. So why it's sort of useful? Well, so this is exercise. Okay, I'm giving you as an exercise. Well, this implies, like we did before, so sine of x is between modulus x and minus modulus x, right? Now, uh, it's clear that when x goes to 0, absolute value of x goes to 0. When x goes to 0, absolute value of minus absolute value of x goes to minus 0 at 0. So this means by sandwich, this goes to 0. So by uh, sandwich theorem. Okay, so we'll stop here.